This chapter is called Volumes of Revolution, so we're going to look at an example of a volume of revolution to get an idea of what it means. So on the left hand side of the screen here, I've got the graph of y equals the square root of x. So what we're going to do is we're going to take some region of this graph, let's say between 0 and 10, and we're going to imagine rotating that blue area that we've just created around the x-axis by 360 degrees. So we're going to rotate it and we're going to get a solid that looks like this. So this is called a solid because it's a 3D shape. If you prefer, imagine that it's filled in rather than hollow. And on this diagram, the red axis is the x-axis. So you can see that we've rotated that blue area around the x-axis like that. So the aim of this chapter is to work out what is the area of the volume, of the solid that we've just created by rotating it around the x-axis. So here we could work out the volume, which is actually given by that expression there in this case. We could also look at a slightly more complicated graph. For example, if we plotted sine x, then we could shade in some region of sine x, maybe 3 of the kind of bumps, and imagine rotating each of those bumps 360 degrees around the x-axis. Then you're going to get a shape that looks a 3D shape or a solid that looks like that. And our aim is to work out what is the area of that entire solid there. So let's try and derive the formula that we can use to try and work out the volume of these solids. In order to do that, we need to have a really good idea of how to work out the area underneath the graph. So we've got some graph here. We don't know what the function is, it doesn't matter. So let's say y equals f of x. And we want to work out what is the area between, say, x equals a and x equals b. So what we're going to do here is we're going to actually think about the trapezium rule. And you already have seen from Maths A level that you can approximate this using rectangles. So what we're going to do is we're going to split this region on the x-axis, this section of the x-axis from A to B, up into even-sized steps. And we're going to say the width of each step is delta x. So let's split that up into, let's say, 3 rectangles. So we're going to draw a rectangle like that. We're going to draw a rectangle like that. And we're going to draw a rectangle like that. And that's going to give us our approximation of the area if we added up the area of each of these rectangles. And we could say, if we wanted to, we could call that x0, we could call that x1, and we could call that x2. Then the height of each rectangle would be given by the y coordinate at each of these values of x. So we could call that y0, we could call that y1, and we could call that y2. So a good approximation of the area, or well, it's not very good in this case because we've only got 3 rectangles, but an approximation would be to say that the area is approximately equal to the sum of each of these rectangle areas added up. So we could write that using sigma notation. So remember, this means the sum of this symbol here, and we want to add up the area of each of these rectangles. Well, we're going to say that the width of each rectangle, we could use any symbol, but generally we use delta x. And delta x just stands for a small value of x. So delta x is the width of each rectangle. So we want to do y multiplied by delta x. And this basically means add up each of these values, y times delta x, for each y value. I guess technically I'm abusing notation here. What I should really put is I want to multiply yi times by delta x, and I want I to go from 0 up to 2. And that's better use of notation in this case, because really what that means is I'm going to substitute in I equals 0 into this expression here. So that would be y0 times delta x. and that would give me the area of that first rectangle. And then next I'm going to sub in the next integer value of I, so I equals 1, into this expression, so that would give me plus y1 delta x, and I add them all up. And then next I'd sub in the next value of I, which is 2, so y2 times delta x, and add up those three expressions. And I'm stopping because 2 is on the top of the sum notation. Don't worry if you've forgotten too much about this sum notation, because you're going to come back to it later on in further maths and do loads and loads of work on it. So, so that we don't get too confused by this little I notation, I'm just going to say the area is approximately equal to the sum of y multiplied by delta x for each of those values of y. I'm going to drop the little I so it doesn't make it too confusing. So this is an approximation. The problem is, at the moment, just like when you do the trapezium rule, we're missing these areas here. So at the moment we've got an underestimate. The way that we can make this better, just like with the trapezium rule, is to make the width of each of the rectangles smaller. So what we want to do is we want to make delta x get closer and closer to 0. So we could say as delta x tends towards 0, this sum of all of the rectangle areas gets closer to the area. That's what this means. As delta x gets closer to 0, this sum gets closer to that true area. Another way of writing this would be to say that the area is equal to the limit as delta x gets closer to 0 of this sum of each of the rectangles. That's how we read that. It's exactly the same notation that you use when you do derivatives from first principles. The limit as h goes to 0 in that case. And well, we need, in further maths, we need to recognise what this is. So if you've got the sum, and inside the sum you've got delta x multiplied by something, and we're making delta x get closer and closer to 0, then that's the definition of an integral. So this is actually the integral of y dx, which is why we use dx, because delta x gets closer and closer to 0. It becomes an integral. And we could put in our limits from x equals a up to x equals b. So whenever you see a sum, whenever you've got a sum and you've got delta x inside the sum and you're multiplying something by delta x, and we want delta x to get closer and closer to 0, that's the equivalent of doing this integration. Next, let's try and apply it to an area then, a volume. So we've got this function y equals f of x, and we're going to imagine taking this region from A up to B and rotating it around the x-axis. So really we've started with a graph that looks something like this, and we've put in a dotted line at A and a dotted line at B, and we're going to imagine rotating this whole area around the x-axis by 360 degrees, and it's going to create a 3D shape like that. So we're going to do a similar thing that we did before, and we're going to try and derive a formula for the volume. So the volume is approximately equal to, imagine splitting this volume up into lots of different cylinders, and the height of each cylinder is delta x. So one way of approximating the volume of this shape would be to add up the volume of each of these cylinders. So the formula for the volume of a cylinder is pi times radius squared times by the height. So pi times radius squared. The radius of each cylinder is going to be the y-coordinate at each value of x. So the y-coordinate is, we're just going to write as y squared. I really should use yi just like we did before, but we don't need to because it just makes it unnecessarily complicated. So we've got pi times by the radius squared times by the height of each cylinder, which is delta x. Because we've split this region up into cylinders of size delta x, of height delta x, just like we did in the previous example. So same as before, this is going to be a better approximation when we make delta x smaller. So as delta x gets closer and closer to 0, the sum of each of these cylinder volumes gets closer to the actual volume. So we can say that the volume is actually equal to the limit as delta x gets closer to 0. So we want delta x to get closer and closer to 0, and that will give us the volume of this sum here. Well, we've got that situation here where we've got a sum and we've got delta x inside the sum. So we know that we can turn this into an integral. So this is going to be the integral of pi y squared dx. And we should put in the limits from x equals 0, from x equals a up to x equals b. So in practice, we're just going to use this formula and we're going to remember that formula, and we don't need to go through this process each time. It's important when you're trying to remember this formula that you get pi y squared, because what you're really doing is pi times by the radius squared, and the radius is given by y of each of these cylinders. Let's have a look at example 1 then. So we've got this graph of y equals 9 minus x squared, and we've got this region obviously between x equals 0 and x equals 3, because that's the root of the graph. And we're going to rotate this region R 360 degrees, or 2 pi radians, around the x-axis. So it's a little bit hard to draw, but we're imagining creating a solid that is going to have a shape something like that I'm drawing here. Okay, so we're making almost like a bowl shape, and all we need to do is try and work out what is the area of this solid that we create. So we could just go straight to the formula, and we could just say, well, the volume is going to be equal to the integral of pi y squared dx, and our x limits are 0 up to 3, because they're our limits for our region that we're rotating around the x-axis. If you forget that formula, then you could go through the process that we went through previously. That's why I like to go through the process, because I think it's useful, because I can never remember the formulas. So I'm going to imagine splitting this solid up into lots and lots of cylinders. So I'm going to draw one of those cylinders in, and the width of the cylinder is going to be delta x, and the radius of the cylinder would be y, the y value at that specific value of x. Technically I should say yi, but I don't need to make it more complicated. So the volume is going to approximately be equal to the sum of each of these cylinder volumes. So the volume of each cylinder is going to be pi times by the radius squared. The radius of each cylinder is y, times by the height of each cylinder, which is delta x. And I want delta x to get closer and closer to 0. So as delta x tends towards 0, the sum that we've got here is going to become the integral. So the sum of all of the cylinders will be the integral of pi y squared dx, which is going to be equal to the volume. So let's use this formula then. So it's just a case of basic integration now, really. So we just sub in our value of y. So we've got 9 minus x squared squared. Don't forget the y squared. Lots of times in exams, people in the pressure of the exam just write pi y dx. It's pi y squared dx. And a lot of the time, actually, I put on my first time I write down the formula x equals 0 up to x equals 3. The reason why is because we're also going to rotate around the y-axis, and it can be a little bit confusing to get the limits right. So here I've got a dx integral and I've got x limits, so that's correct. Because in another section of the course, we're going to have y limits at some point. So now we've just got to sub in or try and integrate this. So I'm going to take pi out of the integral, and then I'm going to expand the double bracket. So we're going to have 81 minus 18x squared and plus x to the power of 4 dx. Okay, let's integrate it then. I'm going to leave the pi outside of the square brackets, and when we integrate we'll have 81x minus 18 over 3x cubed plus a fifth x to the power of 5. And then I just need to sub in the limits. So we're going to have pi multiplied by, I'm going to sub in the top limit, so 81 times 3 minus 18 over 3 times 3 cubed plus 15 times 3 to the power of 5, and then minus, sub in the lower limit. If I sub in the lower limit, I just get 0. So if we work that out, we get 648 over 5 pi. So that is the volume of this solid that we get when we rotate that region R around the x-axis by 360 degrees.